Hello students, welcome back. Previously, we completed establishing the whole number system. Remember, we defined recursively like this, or equivalently using the successor operation like that. They're the same, they're logically equivalent as well. The first viewpoint is more convenient, getting the order relation, and because of the construction, W is well ordered. Every non-empty subset has the smallest element. The latter convention using the successor operation is more convenient, defining the algebraic operations, addition, multiplication, and power operation. All eventually are coming from some kind of repetitions of successor operations. So they're all well defined, and we can consider the inverse operations, subtraction, division, and radicals. They're not well defined in general, so we may have to extend the number system a little bit, and that's what we're going to do now. First extension, integers. Ready? Here we go. We begin with a Cartesian product, W cross W, and define an equivalence relation like this. A comma B is equivalent to C comma D, if and only if A plus D is equal to B plus C. Now please check if this is indeed an equivalence relation. Reflexivity, symmetry, and transitivity. I'll leave that to you. You must have done it already in Introduction to Proof class as a matter of fact. And then we can consider equivalence classes. We have equivalence relation, so we have equivalence partition, and then equivalence class. Set of all elements of this starting set, W cross W. Oh, excuse me. Okay, all right. Now I'm doing it right. So set of all x comma y from the starting set that is equivalent to A comma B, the representative. And typically we used to use bracket notation for equivalent classes, remember? That's the most typical expression we used to use in Introduction to Proof class. Sometimes we used to use bar notation, but in this particular case, we're going to use this expression, A minus B. So A minus B, eventually subtraction, is actually an equivalence class. Defined like this. And here's some examples. 0 minus 2, and that's equivalent to 2 minus 4, and 7 minus 9, and so on and so forth. How about this? 2 minus 0, equivalent to 3 minus 1, 11 minus 9. There are many more. And they're all the same set, same equivalent classes. Elements are of this form, n comma n plus 2, n plus 2 comma n respectively. So we successfully defined the set of integers. Now we can identify each whole number with the equivalence class n minus 0 in Z, and this way we can regard W as a subset of Z. Now, does it make sense? According to this construction, W is not a subset of Z. Z is a quotient set of W cross W, so they are very different. But we can do appropriate identification. Roughly speaking, this is what we are doing. Starting from W, and then using this equivalence relation, we built Z. And then inside, we have a copy of W. Here we have N. Here, N minus 0, basically. Or it can have other expression too. And then the property of this thing and that thing are exactly the same, algebraically, in terms of order, everything. So we can put this into archive, and you can use this copy, the second version, as the most effective version of number system, and then we can use it from here. Do not completely forget about this. Do not throw it away into trash. Put it into archive. But this one is the one we are going to use from this point on. It's more effective. It's more extensive. It's bigger. It has more numbers in there now. And this kind of process I meant by identification. Some people call it embedding, but I'll say this one and that one are the same. So identification, that's acceptable. Now that we have Z, let's do one more to create Q. We're going to do something similar. Oops. Okay, we did integers, now rational numbers. We got Z and the Cartesian product of non-zero integers. By the way, if you have this X notation up there, that means non-zero integer, non-zero rational, non-zero real, non-zero complex, things like that. So second coordinate is non-zero, and we define the equivalence relation like this. A comma B and C comma D are equivalent if AD is equal to BC. Again, please check whether this is indeed an equivalence relation. The reflexivity, symmetry, and the transitivity. I'm going to leave that to you. And I'm pretty sure you must have done it already in the Introduction to Proof class, either as a homework or in class. You must have done it. And then you can consider the equivalent classes. And how do you represent equivalence class? Typically, you use bracket notation, and that is set of all x comma y from the original set, which is z cross cx, that are equivalent to the representative a comma b. But in this particular case, we're going to use a little bit different notation. Not the bracket notation, not the bar notation either. We're going to use a over b, the fraction notation. So the fraction is actually an equivalence class. Here we go. And here's some examples. Fraction 4/3 is an equivalence class where each element is of this form, 4n, 3n. And then all these are equivalent expressions. 4/3, 8/6, -20 or -15, they're all the same. They're all identical equivalent classes with different representatives. All the elements are the same of this form. Here's another example. They're all the same. All the elements there are of this form. So they are the same equivalent classes, different representatives. And of course, you want to take the lowest terms. Finally, we identify each integer with n over 1, which belongs to Q. This way, we can regard C as a subset of Q. You see, basically, we did this kind of thing. We started from W, remember? And then we used this equivalence class to build Z. And then we can identify a subset of Z as W and share the same property, and then put this one into an archive now. Do not consider this anymore, but not trash it, just archive it, remember this, and then we are going to use more effective one, Z. And then we do the same thing, using equivalence relation. We define Q, And then inside we can define Z. And then, of course, inside we have W as well. And now this is a working version. And this one goes to the archive as well. Version 1.0, version 2.0, now version 3.0 is here. So we use a new version, which is more extensive and more effective. Previous versions go to archive, and then we can use Q here. And then we are going to go to the next step, define R and define C and so on. Let's see, how do you define R set of all real numbers? This time, instead of taking Cartesian product, we take the set of all bounded and increasing sequences of natural numbers. There are many, really a lot. And then let's take an equivalence relation. Sequence Pn and Qn are equivalent if the limit of their general term, Pn minus Qn, that difference is going down to 0. So difference of general terms go to 0. Is this an equivalence relation? Well, you can prove it using the limit rule. Let me show you some examples. Most typical example is a power series with natural base. So in this case, natural number 10 is used as a base. And then we have the integer part here, which is finite series. And then the infinite series part is the decimal part. And then the decimal point here. That's a separator. Make sense? And then this infinite series part can be considered a sequence of partial sums, and that sequence is bounded and increasing. This expression is a decimal expression, and if I take different base, say 2, we have binary expansion. Take it 3, ternary expansion, we have different expressions. Here's an example. The same irrational number pi can be written as 3.14159 and so on in decimal expansion. Or it can be written as 11.01101 and so on and so forth in binary expansion. These two are integer parts. And all these are, I cannot use a decimal part anymore. Shall I use non-integer part? This one is the integer part, and this is decimal part. If I use base 8, we have 3.11037 and so on and so forth. Integer part plus, and not the decimal, but octal part, not integer part. You see, depending upon different natural base, we get different power series, and sequences of different power series, they're all bounded and increasing sequences. And these are all equivalent in terms of this equivalence relation, as a matter of fact. That's how we get real numbers. And then we do the same thing. Constant sequence as a representative. Then this the equivalence class represented by this constant sequence is a rational number. And using those, you can identify a part of the real numbers into Q, so you can regard Q as a subset of R. The previous construction now goes to the archive, and we have the new version.